I'm Cynthia Barnhart. I'm the Chancellor here and Ford Professor of Engineering. And like with the other panels, we will go through and have each one of our guests provide you a brief presentation, and then we will open it up for discussion. So we're going to do this in alphabetical order, and we'll begin with Stephen Boyd, who is the chair of the Department of Electrical Engineering and the Samsung Professor of Engineering at Stanford University. He has courtesy appointments in the Department of Computer Science and the Department of Management Science and Engineering. I won't go into all the various research awards he has, but I will say, relevant to today's theme of teach, he has earned some prestigious awards for his teaching, including the Walter J. Gores Award, Stanford's highest teaching award, and the IEEE James H. Mulligan Jr. Education Medal. Stephen.
Thank you very much. I assume my slides will come up there at some point?
Yep.
Okay. First of all, I should say, surprise, we are your lunch. Actually, you're the ones that didn't head out for lunch or something like that. So let's see if I can make, okay. Oh, no, that's going backwards. Okay, so let me go ahead and start. No. All right, fine. I'll just go ahead and start. I think that's the first one. I should say, first I'll say a little bit about my background, and then I'll explain what I'm going to be talking about. My original training is pure mathematics and super applied EE. I should actually go back. I sat in on the panel this morning on digital humanities. So I actually grew up, and both my parents were English professors. And what the panel brought back to me was the painful recognition for me that the humanities is so much cooler than what we do. Actually, I want to take your class. I want to take all of them, actually. So I want to write Python scripts and compose. Anyway, so for us, it's not anywhere near as exciting. But anyway, sorry, too bad. So I teach big classes on applied optimization, linear algebra, and it's from students with very diverse technical backgrounds, right? So I have to say technical there because it's not really diverse backgrounds. It depends which PhD program they're in, right? So, but it is actually interesting. It's multicultural in a mathematical sense because we have people who come from a lot of different areas. They speak a lot of different dialects. Actually, most of them don't think they speak a dialect, and I'll have to tell some of them, oh, by the way, you're speaking a Hick dialect, a mathematical Hick dialect. And what I'm going to talk about, the courses that are, that are mathematical type courses, actually not in math, but typically in engineering and science. So this would be things, most courses in electrical engineering, computer science, mechanical engineering, aeroastro, statistics, machine learning, econ, all these kinds of courses. So anyway, so not anywhere near as interesting as glassblowing or composing or Victorian literature, but that's just what it is. Okay, so the first thing I'd like to do is I'd like to change the title. I actually prefer the title, Teaching Science and Engineering with Computing. And this one is long-winded, but I think it actually says better what we really want, which is teaching computational thinking and doing, that's going to be a big theme, in science and engineering. So that would be my preferred title. No disrespect meant, by the way, the choice of the title. And now I've gone to some other random, okay.
That's the price you pay.
Okay, yeah, this is, okay. All right, so now I'm going to state what is completely obvious, which is that what computing does when you wrap it in with these courses is it makes them actionable, right? So it means you can actually do something. And it means that beyond gaining insight and understanding, students can actually do practical things, and you can do it pretty soon, like we saw something approaching music in 5 minutes, right? So it's actually just like, that is a huge big deal for these courses where a colleague of mine, Bob Dutton, referred to our EE curriculum. He may still refer to it that way. He said it's a deferred gratification with nothing at the end. It was actually pretty good. It was actually a pretty good description of our EE curriculum, right? That, you always take a class and students say, can I do something with this? And you're like, no, just wait for another 4 years, then you'll be able to do something. And then they come back as a senior. Can I do something? No, not yet. So anyway, all right. What's very cool about this, it means that in these classes you can bring together a lot of different ways of knowing. You have the ideas. So what are the ideas? This is with no math. You would have the theory, so you'd actually tell people about the math. You'd say these things are just true. If you believe this hypothesis, then this has to follow, period. That's the math or the theory. You would have things like the practice. Does this really work? How do you do this? And then you have what we call like the practice street fighting tricks. Like, okay, here's something. This actually works in practice. No one knows why, but it does. Okay, so that's street fighting. So we have all these different ways of doing this, and of course this is enabled entirely by the computing. And it's also very nice because it brings a maker culture to mathematics and applications, right? So what's kind of cool about that is you're very jealous of our friends in mechanical engineering. They sit there, and the freshmen sit there, and they do some CAD stuff. And then they press a button, half an hour later, this thing comes out of a 3D printer, and it's like, cool. And then you think about the classes we teach, and they're like so boring by comparison, right? So it's like we're jealous, but this kind of at least, I mean, okay, it's not origami, okay, and it's not a composition, but it's still, for us, it's pretty cool. We have very low standards. All right. And it also introduces an empirical component to these things, right? So you can teach these classes, you can talk about, various things. You talk about the theory, all sorts of other stuff, and then you can say, let's just try it. Let's just see what happens. And maybe on simulated data, maybe on real data, and that's actually really cool. I'm going to try to press the right button now. No guarantees. I didn't. It was the wrong one. Okay. I'm giving up. I quit. Let's see. Okay. No, look at that. Okay, maybe that's just going to the end. Oh, okay, there. I think I have it. There was a button I hadn't seen here. Okay. All right. So, okay. All right. There we are. I did it. Okay, great. And the 10 minutes is almost over. That's fine. So the idea. Now I'm going to talk a little bit and quickly about some of the things that makes all this possible. So encapsulation and abstraction is extremely important. I think Ellen is going to talk about that. That's very important. It means that you have high-level interfaces that are going to match the ideas and the theory closely and hiding the implementation details. That's very important. So there you really have to accept the idea that you and the students do not need to know all the implementation details. By the way, there's people who think that you do, and they are just wrong. So that's simple. So what it does is it shifts the focus to what you can do with the methods and not the implementation. You may spend some time talking about how it works, but the most important thing is what can you do with this. And this is actually very important because it allows you to create outreach classes. When someone from maybe quite a bit further afield is taking this class, they don't want to know the stupid details of the algorithms. They want to know, that's super cool. What is it? What can I do with it? And how can I apply it in, chemical engineering, for example? Okay? So, all right. Now, the enablers, they were mentioned actually in the last panel. One is kind of obvious, but it's sort of not stated enough, and that is open source non-proprietary software. That's critical to all of this. Without that, you can't do any of this. Software that supports high-level abstract interface to users, like, for example, Julia would be a perfectly good example. You're going to hear more about that later. And actually, very important is cultural. It's a culture of openness and sharing. And so this varies by field, but the idea is that the fields that are thriving, if you look around, are precisely the ones where it is expected that you write a paper or something like that, and everything goes on. You would not dream of writing a paper where there was not associated code that's just openly available to the entire world, period. Okay? In my opinion, not only is that morally correct, it's also a huge advantage to the quality of the teaching and the research and everything else. So, I'll start with some suggestions. So the first is, these are all kind of obvious, but the first is I believe computation should be infused into everything in all of these courses, right? I'm talking about all the way from the lowest level immediate introduction all the way to the most advanced PhD level courses, right? So I think I can't imagine this not improving all of these courses. And that allows you to co-develop these different modes of understanding, the ideas, the theory, the practice, the software, the street fighting tricks. It's great. And I should also say what's very important is when you do have these multiple modes of understanding, it's extremely important to be very clear about which level you're at, right? Was that an idea? Was that a theory? Was that a practical observation, an empirical observation? Or was that actually, for example, a street fighting trick? Those are the ones where I tell the students, don't tell anyone I told you, and I'll deny it if you tell anyone. So, okay. So, in the end, I think what this is basically what I'm describing, which is actually, I think it's done in a lot of universities, certainly at MIT, I know that. But my claim is this is the training that students want and need. And it's the ability to fluently move between, the big ideas, some theory, notice I said I qualified that, algorithms in computation, software, and applications. And what this does is it allows you to go into a whole variety of existing fields, and this is much more important. It actually prepares the students to create fields that don't exist yet. And that is actually what we're training people to do. So when students say to me, oh, can I get a job with this? Yeah, but that's not the point. Can you start an industry with this? And that's the point. So, okay, so I'll quit here, and we'll go on to the next one. Thanks.
So next up, Stephen, maybe you'll have to teach Tony how to use this while I'm introducing Tony. So Tony DeRose is an educational consultant. From 1996 to 2018, he was a senior scientist at Pixar, where he led Pixar's research group. Previously, he was a professor of computer science and engineering at the University of Washington. So over the past 7 years, he's developed several initiatives to help make math, science, and engineering education more inspiring for middle and high school students. So please welcome Tony.
Thank you. And thank you for being here this morning, as opposed to, I don't know, maybe listening to Michael Cohen's testimony in front of Congress. So thank you for the introduction. Thank you for the invitation to speak here today. I may be the only one talking about education below higher education. So I'm really interested in K-12 education, general public education. I've primarily been focusing on middle and high school for reasons that we'll talk about in a couple of minutes. And the most visible projects in those lines that I've worked on are two. One is the Science Behind Pixar, and the other is Pixar in a Box. So these are kind of companion projects, both intended to bring some relevance and inspiration to a lot of the material that students are learning in class. We feel like, and there's a lot of evidence to show, that students don't learn if they're not engaged. If they don't see a reason for why to learn something, it's hard for many students to really take interest. And so that's the end of the spectrum we've been focusing on. The Science Behind Pixar was a collaboration, about a 7-year collaboration actually, with the Museum of Science right here in Boston. It opened here in the summer of 2015. Did anybody manage to see it while it was in town? Great, a few of you. It's a 13,000 square foot exhibition that really shows how much math and science goes into the storytelling that we do. Back in the early days of Pixar, we were viewed primarily as a technology company that happened to tell stories. And then the stories became so successful, and the films became so successful that we became a film studio, and people kind of forgot about the technology. And so this is an opportunity to share that with people. It's got dozens and dozens and dozens of activities. Some of them are screen-based like this one. Others are physical. There's video. It's a physical experience, so you go, typically family units go together. There's a lot of really wonderful intergenerational learning that goes on. It's generally the younger guests teaching their grandparents how computer graphics works. And that was a really great collaboration. We know the business of making films. We have the domain knowledge about how math and science and engineering is used to tell stories. And the team at the museum really understood how to take all those complex ideas and package it in a way that is consumable by the general audience, the general public, so ages 3 and up, really. Partway through that project, we realized if we could find a partner in the online education space, we could bring that sort of story in a virtual way to potentially many more people and for free. And so we went knocking on the door of the Khan Academy, and they said, yeah, let's partner to put this together. So we had funding for 3 years that we call these seasons. So season 1 was really focused on math topics primarily, season 2 on science, including computer science, and season 3 focused on arts and humanities. So we're really trying to help answer the question, why do I need to learn this stuff, and what's going to keep it from becoming boring? The math and science lessons, there's 24 of those in all, and they basically have the flavor of each one kind of picks a different creative challenge faced at the studio, and then demonstrates how math and science concepts are used to address that challenge. So there's a lesson, for instance, on the water in Finding Nemo and Finding Dory. How do we create the water? There's a lesson on creating the beautiful landscapes in Brave, and it turns out parabolic arcs play a huge role in that. Each blade of grass in the forest is a parabolic arc. So why do you need to learn about parabolic arcs? Well, making grass. Each of the lessons is hosted by one or more Pixar employees. We really wanted to give a personal face to this material. We also wanted to put forth what's kind of an aspirational sense of diversity. So the diversity of the hosts doesn't accurately reflect the diversity of the studio at large, but it's sort of what we're shooting for. So for instance, Fran hosts a couple of lessons, one on combinatorics and how to use combinatorics to create the robot armies in WALL-E. Alonso Martinez, who's a character modeler, Susan Fong. This is also a chance to do some career modeling. Each of these people is involved in a career that most people don't know about. Fran's a great example. She had interest both in computer science and clothing, fashion. And at Pixar, she's been able to put those two disciplines together. She's a digital tailor, right? Who knew that digital tailors was a career, and that you could be very happy in? I thought what I'd do next is jump over and try to do a quick demo. Showing is better than telling. So the content of Pixar in a Box is it's video content, typically 3 to 4 minute tutorial videos featuring people. There are some exercises that help students demonstrate mastery. And then there are a lot of interactive applets, many of which are patterned after the tools that our artists use. So in the animation lesson, for instance, the creative challenge is, how do we bring our characters to life with motion? It turns out polynomial functions play a huge role in that. These math and science lessons are typically broken into 2 parts. There's a part 1, which is more middle school oriented, where knowledge of that creative challenge is deepened. And there's an interactive that goes along with that here, which is, my challenge here is to make this ball bounce. So I've got a little timeline. And then I have access to a Bezier curve editor here, which again is patterned very much after, if I can grab that, it's very much patterned after the artist tools that our artists use. Let's see if I can get that to play. Yeah, there it goes. So that I'm controlling the height of the curve. At this stage, students are thinking of themselves as content creators. They're not worried so much about how the technology works. And that's where part 2 comes in. It's the second part of the lesson. They're typically more oriented to high school level. This is where computational thinking and algorithm design comes in. And so we walk them through what's known as de Casteljo's algorithm for constructing Bezier curves. And there's a bunch of interactive elements and exercises that help them experiment. Let's see if I can grab that. Help them experiment with how this algorithm works. And by the end of this lesson, these high school students really understand cubic polynomial curves and how they're used to create animation. There's a lesson on how we brought Merida's hair to life in the movie Brave. We use a mass spring system underneath, so her hair is being simulated. There's a physics simulation. And we give students access in lesson 1 to a simulator. And at this stage, they're basically operating as a technical artist. So they're working to dial in parameters to get the kind of creative look that the director might be interested in. And then in part 2, we kind of go behind the scenes and, well, what does someone writing this simulator need to understand? And that's where we bring, in this case, the laws of physics to bear, along with a computational framework. Let's see if I can restart this. So there's a little simulator here that's running live. And the Khan Academy CS platform is really kind of nice. You can interactively manipulate parameter values to see what effect it has on the simulation. So they're hopefully building up a bunch of intuition for how these ideas work, but they're doing that in the context of solving a creative challenge and in the context of storytelling. So I will stop there.
Thank you, Tony. Next up is Alan Edelman. Alan is a professor of applied mathematics and a member of CSAIL, the Computer Science and Artificial Intelligence Lab here at MIT. He's passionate about the interactions between classical computer science and computational science, and is a founder and chief scientist of Interactive Supercomputing and Julia Computing, Inc. Thank you.
Thanks very much. The previous speaker, Dr. DeRose, was talking about for younger students, but I'm already ready to go to infinity and beyond in the higher education. So when thinking about education for computational science and engineering, I was thinking about, do I talk about the math or the software? Because in my lifetime, it's always been math and software and the interactions between the two. And then I thought about it and I realized that, you know, to first order, MIT is the Massachusetts Institute of Applied Math, so I don't have to talk about math. I think math everybody's sold on. So I'm going to concentrate primarily on software and the interactions with mathematics. So I've got one slide talking about computational science and engineering and a kind of prediction for the future, and then the rest of my slides are going to be about software and its interaction with mathematics. So, hey, that works. I got the right button. So computational science and engineering goes by the name of CCE here at MIT, the Center for Computational Engineering. What is it? Well, it's actually, it's in a lot of places at MIT. It's computation that involves the physical universe, whether it's in biology or chemistry or aeroastro. It's literally pervasive around MIT. What I like to say is that, of course, we know why it's important, because the physical world is the world we live in, and many of our problems are the problems of the physical world. And when I look at today's machine learning, which is exciting everybody these days, I tend to think of it as sort of the big data machine learning. It's the forget about anything about the physical world, just take the data, which of course may come from the physical world, but in the end it's the data, process it through something like a deep neural network, which is kind of a big overgrown line fitting, really. It's a regression problem, and see what we can get. All right, and we're doing a lot of things these days with this technology, but we're not bringing in the physical world as much anymore. People are trying, there's a lot of good work coming on, but I think, and this is my prediction, that there's going to be a lot more machine learning in the physical world in the future, and I think it's going to even have a rather different kind of character than the kind of character of machine learning of today. And I would love to see this happening in the College of Computing and the Schwarzman College. I'd like to see it happen through our students here at MIT. So that's my first prediction, and now I'm going to get into the teaching. So I was very happy to see that our president talked about bilinguals at MIT. I kind of feel like I've been a bilingual much of my career at MIT, or a multilingual, and we certainly, everybody else has been talking about multilinguals, and of course this is the right way to go. And so here's sort of an outline of some of the slides that I'll be talking about. So let me sort of jump right in, though. So Professor Boyd already mentioned abstraction. The problem with talking about abstraction is that it's abstract, right? It's very hard to talk about abstraction. So what I thought I would do is talk about a real example that happened this year. Am I speaking properly in the microphone? Is that okay? A real application that happened this year involving a big climate model, you know, the folks who want to figure out, you know, exactly how global warming is happening. So the climate modeling folks came over to my office in CSAIL, and they brought those scary-looking equations in the upper right over there. My computer science graduate students were like, well, we know lots of things, but we don't know that math. So, but I did what I always do. I said, let's figure out what are the right abstractions. And for me, abstractions are both in mathematics as well as in software. And so I just said, let's talk abstractions. Let's figure out what's the right thing to do. So in talking to the climate modelers, they said, we use abstractions. We use matrices and vectors. They are our abstractions. And then, of course, it became clear there are levels and levels and levels. In this particular, this is a differential equation. It has gradients and divergence and all these scary math words. But in the end, the abstraction, the one that really comes to heart for everybody, are mathematical functions. So can we just get those functions at the highest level in the software? And then you see some Julia code down there, which just does exactly that after a few weeks working with the computer scientists. And it never would have happened by either group alone. It would never have happened. You need to have sort of that combination, but I think everybody's kind of sold on interdisciplinary work now. So I'm going to see if this button still works, and I'll move on to my next slide. So again, a software slide. So I'm going to make up I want to talk about elegance and reproducible science. I'm going to kind of make up a fictitious story about a conference that you might go to. So you go to a conference, and big fancy professor gets up there and talks about his computation. He talks about the math behind his algorithm. He might talk about the physical simulation that he's doing. He might tell you how much time it took to calculate. And suppose a student in the audience is all excited and inspired by Mr. Fancy Professor and says, I want to do this too. Can I have your software? What machine did you run on? How did you do it? And I'm not saying that professors is really snobby. In many cases, the professor actually doesn't know how it was done because his graduate students wrote the software. And he doesn't know, and he doesn't even think it's important. But as far as teaching our students, this culture has to change. The very essence of science, as we all know, whatever it is that makes us believe in science is the reproducibility of science. And so many people are talking about that these days. We really have to change the culture that you can't say that the software is coming out later or, it's not ready yet. It just can't be done. If you're going to publish a paper, it's even the question of whether the paper is the primary anymore or is the software the primary, right? This is already changing, and I think we'll see more changes. And on a completely related note, there's the question about elegance in computation. And so as a mathematician, I've often seen beautiful mathematics that makes me just, feel very happy, and mathematics that's just, nuts and bolts. And it's time that we also, talk about what's really good in computing. When we see an elegant computation, we should praise it, and we should teach students to do really nice computing. All right, now the story of bridges. And so, as I've mentioned, I've been involved with the Julia project. I have it on the back of my phone here for the last several years now. And our Dean of Engineering talks about creating bridges at MIT. And I've had all kinds of interdisciplinary work at MIT. Many people have done it. But the Julia project for me has been a very different experience, and I'd really love to tell you about it. So Julia is happening everywhere at MIT in all of the courses. I asked one of my PhD students to put together a list of sample names. It's not everybody. But you could see that Julia is happening in every department at MIT just about. If your name is missing or your department is missing, please let me know and I'll add it. And I'll also give a plug for Manvita's poster, if you'll see her later today. But I want to say something about how this is more than just, I could build a calculator and mass produce it and give it to everybody at MIT, and I could say, oh yeah, everybody's using my calculator. But there's something different that's happening, and this is what's exciting me more. People are talking to each other across departments. People are using each other's software. And people are building, it's not just everybody doing the same software, reinventing the wheel. People are going bigger and bigger and bigger, and this is really what the excitement is. This is what we want to see from computing, and it's exciting for me to watch exactly that. Okay, and this is my last slide, and this is kind of related to my previous slide, which is the notion of how software software for sure is mathematics gone live. There's no doubt about it, and it's enabling, as Professor Boyd said. But it's actually even more than that. I mean, that's pretty good, that mathematics going live, and we've gone far with that. But it's actually more than that. And this is the sort of thing that I'm not sure I appreciated until just a year or two ago myself, but I'm watching it happen. And the idea is when you can actually compose software, when software can work together with other software, so you really can build upon other software, things that you can't even imagine happening start to happen. So I've got a sort of a bad example, and then I'll give you the more modern good example there. In the box there, I have an example of a homework that I gave in my parallel computing class, the course. This was an old homework. I only did it once. I didn't dare do it again. But what I did was I asked students to download a parallel program off the internet, anything they wanted, and make it run. Sounds simple enough. Okay, 75% of these good, hardworking MIT students succeeded, but not 100. Then I asked them to do two things. You know, you could compute a fast Fourier transform on a matrix and invert it. You know, whatever. And they couldn't do it. Nobody could do it. Nobody could get it to work together. One student finally got it working after the deadline, and he's gone on to become pretty famous in the area. So nobody could do it. And that's a problem. Now, what's happening today, and I'm sort of seeing it in the Julia world, and it could happen in any world that lets software compose, is you could do something like take a machine learning program. Machine learning is built on matrices with parameters. That's what deep neural networks do. What if you're creative? I don't want to use matrices with parameters. I want to think out of the box. I want to think differently. I want to use differential equations. Well, Chris Rackauckas is doing that with the Julia software because the technology lets you. He goes ahead and does it, and they're now using that in customized medicine now to be able to give the correct dosages for individual people. So I'm going to finish with my motto here, which is that when software composes, humans compose. And I literally mean working together and being creative. So thank you very much.
Thanks, Alan. So next up is Wendi Heinzelman. Wendi is the Dean of the Edmund A. Hajim School of Engineering and Applied Sciences at the University of Rochester. She's also a professor in the Department of Electrical and Computer Engineering with a secondary appointment in the Department of Computer Science. Her research interests span diverse areas, from wireless communications and networking to mobile cloud computing and multimedia communications. Wendi.
Thank you. It's an absolute pleasure to be back at MIT. I graduated from here a few short years ago. And so it's really nice to be back and see so many professors and colleagues who I haven't seen in a long time. So thank you for the invitation to come and speak. If I can get that working. Where am I aiming this? The big button? There we go. Okay. So I don't think I have to convince anyone in this room, but there are a lot of people who don't really understand that there is basically no field today that doesn't either produce or consume just massive, enormous amounts of data. And that data is really the thing that's going to drive the new innovations, the new insights into those fields. So I loved hearing the example this morning from the humanities about the program that figured out all the words of she and he and him and her in like massive amounts of textbooks. Can you imagine asking graduate students to do that by hand? You know, just 10, 15 years ago, that's what you would have had to do. It's almost impossible. But nowadays, we have the tools and the techniques to be able to gather that data and make key new insights that we could never make in the past. And really, data is the new gold. It's going to be the new thing that is going to set industries apart, that's going to make them be able to come up with new advances and in new techniques. And so it's really important that any student who's educated in the 21st century understand how important this is, understand how to compute on the data, and how to be able to make these inferences out of that data. Now, computational thinking is not just about coding. I certainly think it's important that every student know how to code. And many students, particularly here at MIT, probably all of your students come in knowing coding, whether they're in the music department or they're in the aerospace department. They are tech savvy. That's probably one of the things that attracts them to MIT. But that is not the case in hundreds of universities and institutions around the country where many students come in never having touched a computer before, never having coded. They certainly have their smartphones and they've played on them, but they've never actually done any design, analysis, creation of their own. And so it's really important that we do teach them how to code, but it's also important that we teach them about computational thinking. So it was already talked about abstractions before. I think abstraction is a key concept where we have to get students to understand that there are these massive problems that they're trying to solve. If you can abstract away some of those details, maybe you come back to them later, maybe you don't need to come back to them later, that helps you solve those problems. Same thing with decomposition. If you can take a massive problem and decompose it into manageable pieces that you do know how to solve, and then build it back up together to solve the original problem, again, you're going to get really interesting new insights, and you're going to be able to find new solutions to problems. Obviously, algorithm design, that's sort of one of the keys to being able to describe step by step how you can go about solving a problem or doing something. And then finally, pattern recognition. We all know how important pattern recognition is becoming. We have lots of different AI, machine learning techniques that are basically taking all this massive data and figuring out how to find these patterns and how to use those to predict things going forward. Now, I'm going to talk about a few different models for how we can teach this sort of computational thinking to all students, and in particular, in this panel, we're focusing on science and engineering students. And so, as I mentioned, I feel very strongly that for a student to be educated in the 21st century, they need to have some sort of computing chops that they can go out into the world in. And this is not just about getting a job, but as someone was saying before, it's about how are we going to advance all sorts of different disciplines. Having students educated in these skills is going to make a huge difference. So in the foundational computing model, the idea is that computing is sort of a generic skill that all students need to learn. This is similar to how we've been teaching math in science and engineering over the past several decades, I would say, where in the current model, students take math courses, they take their calculus, differential equations, linear algebra classes, they all take that in years 1 and 2, and then we all build on that. We assume the students know that math, and we can use it in our classes that we teach in the disciplines themselves. You can imagine a similar model in computer science where you have computing skills, very introductory courses that are taught that are open to all students within all of the disciplines. They take those courses, everyone assumes that once you complete those courses, you have the skills, and then you can use those skills in your subsequent classes. And there are pros and cons to this model. So one of the pros is that you're creating a standard skill set upon which everyone can build, and you're providing the education, you're providing the knowledge of these techniques by the experts in the field themselves. Another advantage is that oftentimes students will change their major. They might start as a biologist and decide, I really don't want to do biology, I'd much rather do biomedical engineering or chemistry. And if they have a sort of common skill set that everyone can build upon, they can transfer those skills into the other majors. However, it's really hard for a computing course or any course to be everything to everyone. And so this makes it very challenging for how do you teach these courses that really meet the needs of all the different disciplines. And of course, this creates a very, very heavy load on computer science, which becomes a big issue. The second model is teaching computing as a domain-specific skill, where you're actually teaching it within the domains themselves. And you tailor the computing, the skills that are taught, as well as the examples that are used to the discipline themselves. And this has a lot of advantages in that the domain-specific examples can be really motivating to students, especially students who think, oh, computer science, computing, I have no interest in this. I'm going to be a biology major, I don't need to know this. But if you teach it to them within the context of something they're really interested in, it can be very motivating. It also does distribute the load to teach all of these courses. However, it's very challenging to ensure that you have experts who can teach these courses in all of the different disciplines. And then there's the model of the CS plus X, which I believe there is a whole panel on this afternoon, so I'm not going to go into much detail on this. But this is basically the idea that you take half your courses in computing, half your courses in whatever other discipline you have, and kind of meld those together into degrees. And one of the things I really wanted to focus on is we know that computing in general has not attracted the numbers of women or underrepresented minority students that are representative of the population. And we also know the importance of diversifying our field, because without getting lots of different backgrounds, lots of different ideas, we're going to be missing out on solutions, we're going to be missing out on systems that have inherent biases in them that we don't see because we're not part of those communities. And so it's really important that we diversify the computing field. And there's been a lot of work. I want to call out the CRAW, the Grace Hopper Celebration of Women in Computing, and the Tapia conferences. These are all great ways to create communities among diverse groups of students so that they can feel welcome in the communities and thrive in these communities. One of my concerns is that some of the science and engineering departments are much better at attracting underrepresented students and attracting women in particular. And so the concern is that we don't want computing courses to drive further away some of these students. And indeed, what we'd like to do is create nice on-ramps to computing so that the students who take those courses and say, hey, this is really fun. This is a lot of fun to code. It's a lot of fun to think about database systems. Maybe I could double major in computer science, or maybe I could minor in computer science. We actually could attract more diverse students into computing by offering these different on-ramps onto computing. And in fact, at Rochester, we've done this in trying to create lots of different ways that our students can learn about computer science with zero background, not having any skills in computing in the past. And what we found is that about 30% of our graduating class is female at this point. It's about 33% right now. And about half of those are double majors. So half of them came in wanting to major in something else, tried a CS course, realized how great it was, how fun it was, and then decided to double major in computer science. So I think that there's a real opportunity to help us diversify our field by teaching computing sort of throughout the disciplines as well. Thank you.
Thanks to all of you. That was great. So I think in the interest of time, since what does follow this session really is lunch, maybe I'll just open it up to questions from the audience. Great. Mike?
So one of the things I've been thinking about listening to these talks is that when we want to get computer science used in related fields, how much people from those fields actually need to understand about computer science, right? If I'm a chemist, I assume that I can use a spectrometer without knowing how to build one. And I wonder whether we can get to that point in computing where we've sort of boxed things up enough so that they're just tools that people use versus the need to actually become jack of all trades computer scientists in order to do the work they want to do in other fields.
I know some of you have opinions about this, so jump in.
I think that's, actually, I can't see you. There's a collar right in, okay, oh, so you are here, actually. I guess you couldn't see me. Reciprocity. That's a superb question, and I think actually we have to struggle to achieve that. Actually, it works both ways, right? That how much, I guess the traditional curriculum is that you teach people everything in that field. You start from the very beginning, and then a year later you know a little bit, 2 years later you know a bit more, and you teach them everything. And I think there's a new, actually this also means for doing outreach stuff, you need to condense. It's not like you shorten that. You throw away a lot of that stuff. You abstract it away. So it would be wonderful to have courses, I know they're starting to exist, that teach you just the basics, and a lot of it is obscured. And it's actually okay as a professor when someone says, how does that work? And you simply look at them and you go, none of your business. Yeah. And then you lean forward and say, I'm going to let you know the secret. I don't even know. But it does. So I think it's a very good point.
Wendi?
Yeah, I'd also like to address that. I think that's an excellent point. I think one of the concerns that is not just the case of not knowing how a microscope is built, when something goes wrong, do you know that it went wrong? right? And so in the microscope case, if something is malfunctioning, you're getting crappy data, you need to know that you're getting that bad data and why you're getting that bad data. I think the same thing is true in a lot of computing instances, especially with deep learning and with any kind of machine learning techniques, where depending on the data that you put in, the data you get out is telling you something based on the data you put in. And if you look at it as a black box and don't really understand how it's working at all, you can get into making really bad decisions because you don't understand how it's working. So I think there's a very fine line. I think for sure, and my computer scientists tell me this all the time, it's not that we need to create computer scientists in every field. That's not the case. We don't want people who are advancing the state of the art in computing and designing new algorithms and things like that. We need to get people the skills so that they can use those tools and techniques. And that's a different thing than creating a bunch of computer scientists sort of all across the community.
To address Professor Karger's question, I'd like to say yes and no. So less computer science and more computer science is going to be my answer. Of course, it depends. If the thing that's being built is a tool, then you don't need to know how to do a bubble sort. That's clear. If what you're doing is advancing computational chemistry, say, and you're building a computation on a grid, and so is somebody in EAPS, and so is somebody else, maybe you do need to start to figure out what computer science abstraction that lets everybody work on a grid and not have to reinvent the wheel, or push further ideas. And so it depends.
Another question.
Thank you so much for the talk. So my name is Xiao Yu Wu. I'm a postdoc in mechanical engineering. So I have a question about, because when students, they choose a major, sometimes they believe that they can have better career because of the major, and sometimes they believe that they like this major. So I was wondering, as an educator, is there any difference to treating these different scenarios and how to make sure that they align together? Thank you.
I can address that. I think in any engineering and science field, you're going to have lots of career opportunities. But we deal with this a lot at the University of Rochester with humanities majors, for instance. There's a lot of parents who tell their kids, don't go into the humanities, you're not going to get a job. And we fight back very hard against that, because there are so many skills you get in the humanities that will serve you well the rest of your life. And we have data from our own students, for our alums, that show that your major does matter for your first job, and it has almost no impact after that. So it's more about the skills that you can get in those majors. And so we do try to really encourage students to find what they're passionate about, because whatever you're passionate about is what you're going to excel at. If you don't like what you're doing, even if you think there's a good job at the end, you're not going to do great in it because you don't enjoy it and you're not putting your heart and soul into it. So I think it's really important to make sure students are thinking about what they enjoy, what they're good at, what they want to do, as opposed to just thinking about a job. Now, that being said, I think infusing computation skills into everything is going to make students that much more marketable when they get out.
Thank you. Yeah, go ahead.
Hi, Warren Searing, also from the Mechanical Engineering Department. We've just heard that it depends. How much computer science do you need to know to do something? If it depends, who decides, and particularly, can we trust the students to decide?
Who wants that one?
It's your answer.
I tend to trust the wisdom of faculty and in consultation with the students. So I'll just say that.
Any rebuttal?
I think that's an excellent answer. Faculty in consultation with the students. Sounds like the right way.
Great. Good
Will
question.
Fraser, course X alum. We talked about improving diversity. Before the break, several of us were talking about how computer science is just like mathematics. It's something everybody learns and they infuse it in their work. But by expecting students to be A, skilled in math, B, skilled in CS, we're probably creating some new barriers to diversity, because the reason a lot of students who really have the creativity and such, the problem solving to be an engineer, is they drop out because they can't do the math. And now we're saying, well, you got to be able to do the math and the CS. We know in underrepresented groups, math skills coming out of high school are frequently poor. Now we're saying, oh, and you have to be good at CS too. Aren't we creating some new barriers? Tony, you may want to address this. Others may want to address this.
Sure. I mean, one of the core skills is collaboration, right? And we like saying at Pixar that making a film is a team sport, right? It takes 100 people working together. There are artists that really don't have much technical skill. There are technologists that don't have much artistic skill, but they work together to create these beautiful stories. And so I think the more we can create opportunities for students to hone collaboration, somebody said it earlier, that it's something you have to teach, right? It's not something that's emergent. And so I think collaboration is something we really need to focus on, especially in the context of diversity.
I would also say, again, getting back to this concept of on-ramps, that you have to have ways that kids can get into these fields where they haven't been coding their whole life. And so that's, I think, one of the big turnoffs to many women and underrepresented minorities in computer science is that they're sitting in a class with someone who built their own computer from scratch when they were 10 years old, and they've never done anything. And then you just feel like, hey, wait a second, I'm not good enough. And that's not the case. They just haven't been exposed. They don't have the experience. So if you can create lots of ways, and you don't want to take the person who's been coding their whole life and do it, you don't want to hold them up. So you have to have opportunities for them to go soar, but you also have to have opportunities and on-ramps for those who are not comfortable with this, who've never been exposed, to try it. And they may hate it and go away, but they may love it. And so giving them that opportunity, and I think the same thing is true with math. We've been experimenting at Rochester with creating different types of math courses that are teaching the same content, but maybe slowing it down, having it be utilizing summers. So students do have to stay, and we pay for them to stay over the summer so that they can kind of get caught up with some of the other students who had great math in high school. So we do, it's a huge issue, and it's unfortunately, I think it's something we have to address in the high schools, that we have such lousy math, science, and computing education in so many inter-school high schools, and such great versions of those in suburban, well-off, affluent high schools, that we create this two-class system. How do we address that both at the high school level and then creating on-ramps at the college level?
My name is Kurt Newton. I'm with MIT Open Learning. Reflecting on Professor Edelman, the story you were telling about how you were able to come up with this really fortuitous collaboration between the climate modelers and what you're doing in Julia. How are we doing at people who have those kind of problems that they're wrestling with, finding the resource? How proactive or how intentional are we able to be versus just getting lucky?
Everyone's looking at me again. So, the internet's an amazing thing. And I'm sure we're at the tip of the iceberg, as I think your question suggests, and there could be way more collaborations. GitHub is an incredible thing. People can collaborate online. The Julia project, many people were involved in the creating of Julia who had never met each other until some conference happened. There's lots of ways now, and probably we need to foster that as part of the education until it becomes familiar to everybody.
Any other questions? Please.
Hi, my name is Edith Harrell. I'm a PhD from MIT, from the Media Lab, then a research scientist here, and last 20 years an entrepreneur building technology companies and e-learning, teaching computer science, design thinking, computational thinking. I think that one point about what many of you are talking about is that we want to teach computing in the disciplines, because we heard it in the earlier panel, because it teaches students how to think, how to solve problems, and it's a great tool to think about the discipline in some creative, innovative way. And yes, learning about the disciplines teach the engineers and the computer scientists, give them tools to think about programming and making decisions. And what's lacking is a little bit is how we also orient the students, not just about ethics, but about impact, solving problems that matter, doing engineering and computer science, and using these tools in ways that are actually changing the world. And maybe you can talk a little bit more about that, Wendi, when you're hinting towards starting doing the computer science in the disciplines and the disciplines in the computer science already in the K-12 system, so people can grow and be ethical, but also solve problems that matter and really make an impact on what the world needs now.
Yeah, no, I think that's absolutely key, and I love the panel that we had before on teaching ethics in computing and in all of the disciplines, because if you think about it as an afterthought, you're already using tools and techniques now that are inherently based on a set of assumptions. If you think about it from the get-go, you know, from the start, you're looking at how you create solutions that are ethical. Now, that being said, of course, there's all sorts of unintended consequences, right? And it's going to be impossible to be able to think through all the potential outcomes of technology use in all of the different fields. But if you have lots of different people from different backgrounds coming together to think about these ideas, and I think bringing in the philosophy folks and the ethicists to help kind of formulate even what the questions are, because it's very hard for engineers and computer scientists who haven't thought about this before to be thinking about that. So having those interdisciplinary teams, I think, will help and go a long way towards addressing that concern.
Tony, do you want to say anything about computational thinking in the context of youth storytelling?
Sure. So this kind of comes to the, teaching it from within another domain. So we piloted a CS course with the Oakland Unified School District. It was a middle school class where it was, they have a, teaching how to, build web pages. This was a second class, which was coding for storytelling. And so about a third of the class was walking students through the storytelling principles in season 3. And so they came out of that project, that part of the course, with an original story of their own, with original characters. So really kind of their personal voice that meant something to them. And then the rest of the class was, how do you realize that story in code? They were using code.org, but it could have been Scratch or other things. So it was, I think it brought students that might not otherwise be interested in computing, they're coming from the arts and the humanities, brought them into the field a bit.
Cool. Okay, I think there's one more question, and then we're going to break for lunch.
Hi, I'm Roy McDonald, PhD student here. And we heard about the importance of making sure the software is open source, especially as things become more black box. And I think that's a tradition that looks set to continue. But it seems sometimes that the data required to kind of either put things into practice or push research or play around with your own ideas if you're going to start companies and that kind of things. It seems that data is becoming less available sometimes, especially as more and more of it's being collected by private companies. And I was curious what you think universities' role is in making sure that that's available to students.
Thank you.
I would say that we need to do our best to make this a value, and we should all be talking about this question, about how important it is to have access to data. And very often the very, say, private company that's trying to protect its data, thinking sort of kind of, in its own self-interest, as perhaps companies need to, might even benefit from, in ways they don't realize by opening it up. And so the more stories like that, the more people realize that, the more we all ask for that, the better we will all be.
I think there's also a role for government agencies. So, for example, NSF has a number of programs that is trying to entice, provide funds for faculty, students to create data sets that then have to be open, that are then available for the entire community to build off of. So I think the more that agencies like NSF and NIH really support open access of the data, the better off we're going to be.
I would say one thing, I think your point is dead on. Access to data is public access to data is extremely important, and it's not that good now, and it's getting worse. But I think actually one of the things we'll have to address to take care of that is a bunch of incentive structures in universities, right, and among researchers. So what's wonderful is if you win some fancy prize, or you write some fancy paper or something like that. There are other extremely important artifacts. One is software that we've talked about. Another is data and making it available. These provide incredible value to a very wide range of researchers, and it is approximately not valued at universities. I'll speak for my own, okay? Maybe at MIT, where it's much more enlightened, that's not the case. But I think that's now the good news is that sort of the younger people coming up who will eventually be running things, they're totally on board with this. So it's a very good point.
So we are going to wrap it up now. Please join me in thanking our great panelists.